Good morning, everybody. Welcome to the second lecture of Quantum Transport course. Today we will talk about quantum interference. That's actually, if you wish, quantum, what makes quantum transport quantum interference effect, in fact. Before we talk about interference, we need to do some extra job. You could find it technical, but it's not technical. It just expands our knowledge to more general nanostructures. Namely, we will look at multi-terminal nanostructures, not only two leads coming to this, but more 3, 5, 6, and so on. And we will figure out how scattering matrix works in this case, how Landauer formula works in this case. That will give us a possibility to split quantum waves to arrange circuits, quantum circuits, where electron waves are split. So we will talk about beam split or kind of elementary multi-terminal nanostructure. Good. I wouldn't say anything about Landauer formula today. Rather, I will talk about interference in general, in particular quantum interference, and about phase shifts. Interference actually is a mean to see phase shifts of the waves. Right, it will be just general discussion, and then we will concentrate on manifestation of interference in quantum transport. We will consider two interesting systems, double barrier and Aharonov-Bohm ring. And in the end, I even talk shortly about a couple of experiments, classic experiments, which are first manifestations, first observations of interference in electronic transport. Good. Let me start with multi-terminal nanostructures. Here I've drawn one. So what is that about? First of all, the details of nanostructure are not that they are not important, but kind of can be completely regarded as a case of scattering matrix. So we have a scattering region here to describe any nanostructure. What's important, how it is connected to outside world, and what do you measure? So it is connected to 3 leads or terminals or reservoirs, whatever word you find, whatever shorter or more elegant. Those 3 of them. And one can set voltages of these leads basically independently, right? With respect to some ground, for instance. Good. And then there's current going to each terminal and which can be measured. So that's how we can measure quantum transport in multi-terminal setup. There are n voltages, n currents, n being number of the terminals. Right, so what for goal we will have? Well, we will express currents in each terminals in terms of voltages. If there are no voltages, no currents, and scattering matrix. Right. I also need to mention that also practical case in many nanostructures, even Leo Covenhoven, which is famous Dutch scientist, used to say that this is definition of a nanostructure. This is something which has gates. So I put some gates. But gates didn't have direct electric connection to the structure. There was no DC current going to the gates. So they just change scattering matrix. They don't lead to any extra transport. All right. Everybody understands the setup? Fine. I will go on. Again, I would not hesitate to repeat it again. I really like questions, which you better put to the chat to give me some time to react. Better to have them. Good. Let us see how we can use scattering matrix in this setup. All right. Basically, it's the same scattering matrix. There is a set of waves which come to nanostructure, and there's a set of waves which go out of the nanostructure. And scattering matrix relates these two. It takes incoming wave amplitudes and gives back outgoing amplitudes. It is the same as in a two-lead situation. The difference is that the channels in the scattering matrix are somehow distributed over the terminals. Each channel has a kind of parent terminal. That's why it's better to index the modes, incoming waves, these two indices. So Greek index for time being would mean a terminal, and there's a certain number of transport channels labeled with Latin index in each terminal. All right, so that particular element of scattering matrix describes propagation from the channel N in terminal alpha to channel M in the terminal beta. Scattering amplitude squared of this amplitude would give you probability to start in this particular channel to end up in another channel. Fine. Let us recall general properties of scattering matrix. Let us see how it is expressed in new situation. Let us see. Good. First of all, I want to mention that there's still separation by blocks, and there is still difference between reflection and transmission. There are elements of this matrix. There are quantum trajectories which where electron comes from terminal alpha and gets back reflected in the same terminal. Apparently that doesn't contribute to the current. And there is also transmission when these initial and final terminal indices are not the same. By all means, scattering matrix must be unitary. As we have heard, it just expresses conservation of the number of particles. While in classical world, where only probabilities matter, it would just mean that probabilities probabilities of all reflections plus probabilities of all transmissions is one. Right? In quantum world, this probability should be satisfied for any arbitrary superposition of incoming waves. And that can only be done if the scattering matrix is unitary. Scattering matrix is unitary as Dagger times S is 1. Fine, how to express it in terms of in new situation? Well, I just substitute this double indices, right? I hope you can follow. So this is transposed matrix. Transpositions, complex conjugated matrix. A complex conjugation is Hermitian conjugation is complex conjugation, and transposition of indices. Right. And I just write multiplication of matrices in the form of the sum. That's what I get. Right. What becomes important is the symmetry property of the scattering matrix upon time reversal. We shortly talk about this for two lead scattering matrix. Now let me restart this. So let us look at this expression. You see that indices are permitted on the left and on the right. What does it mean? We start in channel BM and go to channel alpha N. If you reverse time, we start in channel beta M and go to channel alpha N. So that's logical. Also, magnetic field is reverted. Let us recall why. Because magnetic field is readily available in the lab. Readily available mean to remove time reversibility in the structures, right? So magnetic field changes sign upon time reversal, and this is available tool to break time reversibility in electron transport. Fine. Little bit worried that I don't have any questions today. Hope you're not sleeping. Good. So it's just a rather simple extension of two-lead scattering matrix and management. All right, let us understand what we are going to compute before the actual computation, evaluation, derivation, whatever you say. Let us resolve to the case of small voltages where the relation between currents and voltages is linear. Fine, there are n voltages and currents. So there is a matrix which relates n voltages and n currents. Let's see if I have a question. What is the transpose of S alpha n beta m is it S beta M alpha N? Precisely. Yes, so double index, yeah, you don't have to transpose double index. Just it stays as it is. Good. So we talk about linear relation between currents and voltages, and since there are n currents and voltages, we have n by n conductance matrix. So in multi-terminal structures, conductance is a matrix quantity. Let me give two general relations which are not obvious from first second, but are certainly obvious upon third second. And that should be valid for any conductance matrix because it is a consequence of general laws of nature. First law is current conservation. So whatever voltages you put it, the sum of all currents going from the structure should be zero, current conservation. That implies that summation of this matrix over first index should deliver you zero. Fine. Another property which is perhaps a little bit less obvious is the following. Let us imagine that I raised all voltages on all leads by the same amount. Okay, I apply voltage. I didn't apply any voltage difference which can drive currents. So the currents must be zero. In kind of very high language, I would call this gauge invariance. But whatever, it's just rather obvious concept that without voltage differences you cannot derive currents. So in this case, it means that if you sum it over the second index, you also get zero. Good. It gives us a kind of fundamental properties of this conductance matrix, and in practical terms, it gives us possibility of quick, foolproof checks of any formulas about this matrix. All right, let us see. It's time. Is it time for a formula? Oh, okay. I need to mention kind of usual misunderstanding. For two terminals, conductance supposed to be 2 by 2 matrix, but we never learned it at school. Conductance usually just a number. So how come? Because owing to these two, whatever conservation laws, fundamental limitations, 2 by 2 matrix of this sort should have only one parameter. Here I put it. So what does it imply? If I do matrix multiplication, I see that each current is a difference of voltages, and sum of the currents must be zero. Good. Let us see. I kind of have an impression it's all strange with Zoom that I go too fast. Yeah, did I go a little bit fast? Anyway, if you notice something strange about my speed, if I got too slow or too fast, I really appreciate you kind of give me some feedback. Otherwise, without your reaction, it's difficult to adjust the speed. Fine. Conductance matrix, 2 by 2 matrix with a single independent element. Right. And now Landauer formula. So it looks similar to two leads situation, but yeah, of course it does not. It's a bit more complex setup, right? In any case, we see currents, many currents instead of one. We see integration over energies, which means electrons at each energy can contribute to the current. And we also see field factors, which come which shows that electrons actually come from the leads, and there's some electrons in there. Good. We also see, conductance quantum, which, as I said, appears almost every day, almost at every slide in quantum transport course. Good. And that is some quantity P alpha beta, which I find here. It does not stand on my slide, I hope. Who can guess what is this? P alpha beta. Recall kind of two-lead Landauer formula. Recall a picture of electrons which can be transmitted or reflected. Oh, look here. So, ladies and gentlemen, there. Right, Francesco. This is probability marginalized. Yes. Okay. Don't quite understand marginalized, but yes, it is indeed probability. It is a probability to go from alpha, from transmission, to start in terminal beta, right? And that's logical. It comes with field factors in this lead. And go all the way to terminal alpha and contribute to the current there. Right? Good, it's probability, and it does not depend on the channel, doesn't have channel index, because I just sum up all probabilities to start in any channel to end up in any channel. That's what I wrote with this trace. So with this trace, I sum up over channel indices. Oh, this is logical. All right, this term is logical. We have electrons incoming, electrons outgoing. I am a little bit surprised with this term. It also contains probabilities, eventually the same probabilities, but field factor is a field factor of the same lead. So, and it comes with minus sign. So what is this? How one can explain this term? Well, this is clear. Those are electrons which are transmitted from terminal beta to terminal alpha. How about this term? We need to work on go. Yeah. Martin, not going electrons from terminal alpha to any terminal beta. No, that is taken into account by this term. Let us see. This term is minus sign, and it depends on the filling factor of the same terminal. Let me draw it. So that's all other terminals. Look at terminal alpha only. So electron come. Some of them transmitted. Some of them are reflected. And the balance gives me the current in terminal alpha. So what is this? It is, in fact, sum of all transmissions to all terminals by probability conservation. All logical. So this picture explains this. So there's some incoming electrons in terminal A alpha. Some of them are reflected, and the probability of reflection can be expressed through the probability to transmission. Some of them, some of all of them must be 1. Good. We have settled this. We understood Landauer formula, and it's in fact your probability analysis. That's how we got these probabilities in terms of scattering matrix, and yeah, one can run simple proof checks. Current conservation. How to, for instance, check current conservation? Well, we just sum up over alpha. Yeah. Finally, I've got chat window. We sum up over alpha. We sum up over alpha, and then under index of summation, we can interchange alpha and beta, then these two terms cancel immediately. We put beta here, alpha here, and well, they cancel. Probabilities are symmetric. Fine. Let us see. And of course, if all filling factors are the same, there is no current. So we also check second rule. Good, that's Landauer formula. Now we can compute conductance if scattering matrix is known. Let me just make it a little bit more explicit. Like in Landauer formula, we can assume that transmission doesn't depend on energy. We can integrate over energy. Result will be proportional to voltage, and the coefficient is conductance. So here is the conductance. So it is expressed entirely in form of these transmission probabilities. And okay, of course, one can elaborate it for 2 terminals as well, and we end up with the formula which we used before, which was a set of sum up of transmission coefficients. Transmission coefficients being eigenvalues of this squared of transmission block of density matrix. Fine, it is it possesses the following time reversal symmetry. It is a bit similar to scatter matrix. I switch B to B minus B, and I transpose indices, but in this case, there are only terminal indices. One can derive it from properties of scatter matrix, but in fact, this is general so-called Onsager symmetry relation. Just wonder how it is taught nowadays. Has anybody heard about Onsager symmetry relations for kinetic coefficients for response functions? Yeah, nobody. It is a funny property, and it relies on the presence of thermodynamic equilibrium. So if you measure these conductances in the system which in thermal equilibrium, then if there's no time reversibility, the matrix of conductances is symmetric. If there is a factor which changes this time reversibility, then anti-symmetric part of conductance matrix is just proportional, is odd in terms of this factor. Good. This is valid not only for conductance, but for any linear responses of any system in thermodynamic equilibrium. I guess I must insist that you hear about something about this in the course of thermodynamics. It's funny thing, but yeah, if you don't recognize that Onsager relations hold, with some fantasy, you can easily make whatever perpetuum mobile can get energy from nothing. Onsager symmetry relations, in our particular case, it means that if time reversibility holds, conductance matrix is symmetric. Anti-symmetric conductance matrix is a manifestation of the broken reversibility. For instance, in Hall systems, Hall effect, for instance, is an antisymmetric conductance. Quantum Hall effect, it's ultimately antisymmetric conductance. There are examples which involve magnetic field. Fine. That was about Onsager. Well, just to say a part where I like to talk about persons. Onsager was really very unusual, perhaps greatest man. He got the Nobel Prize, and journalists wanted to call him to take interview, and they get to his wife. They told her, well, your husband just got Nobel Prize. And the response was, in which subject, physics or chemistry? Right? So it's of course it's of course wonderful that you can be productive in many areas, but I guess the real reason for that is that you have a partner which supports you to this extent and really believes that you could get Nobel Prize in both areas. Fine, Ansager symmetry relation, and I would like to move forward. And we come to splitting the beams. So our beams are electron waves. So let me describe an elementary nanostructure where we can split the beam. So it has 3 terminals. And what is this? It is not a general beam splitter. As you can imagine, I pretty much fixed all scattering matrix. What do I, why do I do so? I want to mimic a kind of optical beam splitter, one of the usual designs of optical beam splitters. So it can send electrons and can also send, make a whatever prism and send actual optical waves, beams. Right, and what is specific for this beam splitter is that if I send a wave to this end, 3, it will go to channels 1 and 2 with equal amplitude and nothing will go back. How can I see it from scattering matrix? Look at this row, right? This means no reflection. This means transmission amplitude to 1, transmission amplitude to 2. We square it, we have 1/2 equal probabilities to go to go up or to go down. Fine, that's what it does. It looks pretty symmetric, and very naive expectation would be that this beam splitter would work, would do the same in all directions. Kind of could come from terminal 1 and go with equal probabilities to here. Nor it does not do so. Let's look, for instance, at this row. What does it mean? There's a probability 1/2 to be reflected, and probability is 1/4 to go to other leads. All right. One could think it's just a faulty design. Perhaps one can make it better and provide fully symmetric reflectionless beam splitter. So with all zeros over here. But if you try to make up such matrix, it doesn't satisfy whatever general it is. It doesn't satisfy unitarity requirement. One could kind of make an exercise out of that. So there are no really fully symmetric reflectionless beam splitters. Fine, so we need this element later when we discuss quantum interference. Why is it so? Because we want to split the waves, let them go by different passes and then combine this. And for those, we need splitters, and each splitter can also combine the waves coming from these 2 terminals. Fine. Let us see. We know scattering matrix. Let us, as an exercise, compute conductance matrix. Oh, we know how to do this. We compute probabilities that will be for non-diagonal elements of this matrix for unequal terminals. Those are just probabilities to go from one to another terminal. And to get diagonals, we need to use a formula to basically to sum up these elements. Fine. This is conductance matrix. So it can be treated as any other nanostructure. And you see the conductance matrix is symmetric because there's no magnetic field. These elements are precisely the same. Good. So we still have some minutes before the break. Let me talk about interference in general. That's kind of indeed the discussion which can be made very general but still useful. Let me start as follows. There are many stupid pulse tests, whichever interviews, and once somebody has interviewed physicists, yeah, that was a poll about what would be the most famous and influential experiment in the history of the whole physics. Yeah, of course, correct answer is, the correct answer. It is my experiment or experiment which I just will do in future. But surprisingly, many people gave the same answer. That was the winner of this poll. It's a double slit experiment, which in some ways has been done in the 18th century, but still kind of useful and valid, and still is repeated in one or another setup. So let me tell about this experiment. We have some waves. There must be waves because they should have phase. And but it doesn't matter whether it's quantum electron waves or optical waves, but just some waves. And we emit these waves from point A, and we look at their intensity at point B. So in fact, it's probability of propagation from point A to point B. All right. And how to figure out what is this? We have two slits, and we have two contributions, two ways to go from A to B. It means that if we consider an amplitude to go from A to B, we have two contributions from two passes. Okay, we got amplitude. To get probability, we need to square it. That's what I do. And then kind of the experiment is in fact expanding the squared. If we expand the squared, we find squareds of amplitude first, right? And they are associated, as we can see from this expression, just with probabilities to go either through first slit or through second slit. But it's not all. There is a term which doesn't exist for classical particles. There's a term which shows wave nature. And okay, that's how I write it. It's a real part of two amplitudes. So it depends on the phase shift between the amplitudes. Right. So how would you see it in optics? For instance, one can move point B, and that will change the phases which are accumulated on both passes and will give interference picture. Or one could put something onto the path which will change the phase of the wave while not obstructing its propagation. Right, so you can only change phase by any means, and you change this interference tone. Is it all clear about this experiment? That should ring the bell to some extent. If there are any questions, I would be happy to answer. I could even explain why this experiment is so great. If not, let's have a break for 9 minutes. So we come back at 9:30. Sorry, 9:40, of course. It's time to go on. Fine, so we have double slit experiment. Let us see, we understand that crucial here are phase shifts. So that doesn't modify probabilities to go by two passes, but shifts a bit the phases, so you can see the interference. Let me now discuss how one can get phase shifts for electron waves which propagate in nanostructures. Let me first consider scattering without reflection. You remember adiabatic quantum transport, electrons wet through a waveguide of complex shape without reflecting back. If it's smooth enough, let us assume that we have some potential which is smooth enough. Let us see what we have in this case. In this case, the wave function would keep the same magnitude. So it will be purely phase vector. Phase vector which will depend on x and the coordinate. Right. Let us now recognize that it is similar to usual vector, but with k which depends on x. So local derivative of this phase here would give me local k wave vector which will depend on x. What is this local wave vector? Well, that can be figured out easily. That can be figured out from energy conservation, right? So potential energy is different, and the total energy E stays the same. So there must be change of wave vector. Fine. What does it mean? It means that if we change potential in some region, and even if this potential does not give rise to reflection, scattering, it will modify the phase of electron flow. Good. It's interesting to discuss energy dependence of this phase. So how do we do this? Well, we just take this and we differentiate it with respect to energy. And if we differentiate this with respect to energy, what we get is inverse velocity of a particle. Good. It's K. We need to integrate K to get change of phase. And we will figure out that eventually time derivative of phase with respect to energy is related to time, which is required for electron to cover certain region. Fine. So there is, for any nanostructure, there is relation between phase shift and scattering phase shift, and how much time particles, electrons have been there in this nanostructure. Fine. Voltage dependence. I'm talking about dependence on the gate voltage now. So let us see, we do the same. Basically, we expand it in terms of small voltage. This expression, that's what I have. It is again inverse velocity. So the total shift is roughly voltage times time. Yeah, I need to divide it by h bar to keep it consistent. Fine. So we understood that the phase shifts can be provided by just changing potential, and it doesn't require any classical change of electron trajectories. It doesn't, this potential doesn't result in reflection, transmission, right? It just changes the phase. What is typical for this mechanism? There's time reversibility. Potential doesn't change sign if time is reverted. That's why if you go from point 1 to point 2 and from 2 to 1, you acquire precisely the same phase shifts. That's what I put here. Good. That's phase. I would use letter K for these phases. And right, kind of God made physics and its opponent apparently made notations for us. Good. So this phase is called dynamical phase. I don't know how to explain this, but it's just what people use. Dynamical phase. Fine. And that's very interesting alternative way to get phase shifts. Those are phase shifts which are acquired when charged particles propagate in magnetic field. All right, to get a kind of a Gaspar need, let us see, a trajectory magnetic field, and we can integrate over to get the full phase on there. We can integrate over elements. So at each element we have momentum, which is wave vector. I divide it by h bar, and in the direction of propagation. Fine, that gives a full phase. Now I need to recall some formulations of classical mechanics in the presence of magnetic field. And formulation is I wonder if you remember this or not, or have heard about this or not. This is actually a question to answer in chat, but I will tell you, it looks like elongation of the potential, of the momentum, sorry. So if one changes magnetic field, the momentum gets extra term, which is nothing but vector potential um, due to this magnetic field. I put it in CGS system. Yeah, I guess in C systems, it comes without the coefficiency. All right. Yeah, I still waiting for answers in the chat. Have who of you? Okay, Francesca has seen this derivation. So it comes from classical mechanics when you want to put magnetic field not in the form of equations of motions, but derive it from Lagrangian or Hamiltonian. Then you need to put a vector potential there. Fine. So what does it result in? There is a phase shift which takes up this vector potential of magnetic field and integrates it over trajectory. Yeah, as I have repeated many times already today, magnetic field is invariant with respect to time reversal. This means that if we take the same trajectory in opposite direction, we got the opposite phase shift. Right. So it's called okay. It is another source of the phase, and you might guess how it is called. Nobody dares. I also would not really figure this out. It is called geometric phase. Okay, dynamical phase, geometric phase. Fine, and no, yeah, it's definitely not a Barry phase. It is called geometric phase. Again, geometry does not mean much in this. Right now, I am about to describe one of the most wonderful, spectacular effects in the history. It's perhaps even for me, it's even more striking than to slit experiments. Although, yeah, it actually might require two slits as well. Good. So what we're gonna do, we wanna have influence of magnetic field on electron propagation without having actual magnetic field. So we talk a magnetic coil with the axis perpendicular to the plane of the slide, right? We put some current. So there is magnetic field only inside the coil. There's no magnetic field which comes out of the coil. Right, and we want to make a simple interference experiment. Okay, let me put two slits over here. So there's one possibility for electron go above and another possibility is go down. These two trajectories interfere, and what is the difference of phase shifts which enters the probability. It's a difference of phase shifts accumulated here and here, and it is actually the phase accumulated along the trajectory which just makes a round about the coil. All right, so there is a counter integral over vector potential, and that can be related by Stokes theorem to full magnetic flux through this trajectory. So there is, let me draw a trajectory, whatever it is. Magnetic field perpendicular to this trajectory contributes to total flux through this. And the flux is the flux enclosed in the coil. Right, here I put it. Right, this phase shift. And I wanna use interesting quantity, flux quantum. To, yeah, phase is dimensionless, flux has dimension. So it is a phase effect produced by flux in units of flux quantum. Right, phase is periodic, kind of if one changes phase by 2 pi, nothing happens. So result of interference is periodic in flux. That's the way to distinguish it from many other effects. Okay, spectacular thing that there is no magnetic field acting on this trajectory. So classical particles just don't feel anything. They wouldn't change their motion at all, right? But quantum particles do feel vector potential, and it gives rise to this spectacular interference effect of into magnetic field, Aharonov-Bohm effect. Fine. That was general physics. I'm ready to come to quantum transport. There is a question. Let me look at the question. In case of the dynamical phase shift, there is no money sign. Is it correct since the voltage difference changes sign when the direction is different? All right, perhaps I missed some important point in my explanation. Let me go back to the slide and make a simple drawing. So it's about dynamical phase. Was about this. This voltage is due to gate voltage. It's not voltage difference involved. So there's electron. And there's some gate electrode, which influences it. So the potential, which is felt by electron as function of x, looks somewhere like this. And this is what I take into consideration. So there is no voltage difference. Indeed, voltage difference would change the sign. It's just voltage itself, potential energy. All right, Baron, does it answer your question? Right. Let me go forward. Yeah, I told about the Aharonov-Bohm effect. Let us now go to interference in quantum transport. And I would like to talk about very, very generic and interesting system about double junction. So in this story, we just have two one-channel scatterers and would like to combine them to put them in series as it is shown. So there's a scattering matrix of left scatterer, scattering matrix of right scatterer, and we will compute in a minute the answer. What a simple thing to be surprised of. When combining things, you expect that the result will be kind of function will be determined by properties of the things you combine. Okay? Everybody agrees with me? But in fact, it depends on tiny cultural differences. There are cultures where this rather postulative thing is doubted. Example is Russian culture. My mother tongue is Russian, and I used to be exposed to a simple and stupid riddle, which actually gives much insight to quantum physics. Let me tell you this riddle. A and B have been sitting on a roof. A has fallen down, B is fallen down. What is there on the roof? I reckon nobody of you speaks Russian. Otherwise, somebody would give you the answer. I shall give you another second to get the answer. A and B have been sitting on the roof. A has fallen down, B has fallen down. What remains there on the roof? It is apparent and remains on the roof. Good. So the sum of constituents sometimes is not defined by constituents, but something which combines them, something which unites them. This end. What is the end in our particular case of quantum transport? When we combine these scatterers, the space between them, no scattering could take place in this case, in this space, but electrons going there can accumulate phase factors. Here it is. So I have at the moment dynamical phase only. So there are phase shifts accumulated along these passes. Well, now let's get our hands dirty and let us compute the propagation through the double barrier. What is the simplest story which can happen to electron? All right, it can transmit first junction, go to the second junction, accumulate phase shift, got transmitted through the second junction. All right, so this is a contribution to total amplitude, and I need to multiply all partial amplitudes for each elementary process. That's what I do. Left amplitude, transmission through this empty space, through this end, right amplitude. Good. That's one possibility. Another possibility, it's a bit more complex. I put it here. So get transmitted, get reflected from the second junction, get reflected from the first junction, and finally transmit the second junction. What does it give? Well, again, I need to multiply all partial amplitudes through the left, phase factor, transmission, reflection, phase factor, refraction from the left, phase factor, transmission. Okay. Then I understand that I have infinitely many possibilities of this kind. Those differ by number of bounces between the junctions. One bounce, two bounces, and that's it. And each bounce actually gives this factor. Right? So what I have here is a case of geometric series. Again, geometry has nothing to do here. You might remember it's a series which looks like this. One factor, another factor, yet another factor, and so on. Right? Who can give me the answer? I guess it makes sense to speak up. It's not really convenient to write formulas in the chat. Oh, nevertheless, you manage. Yes, right, good, great. That's what we know. It's 1 minus alpha. We apply the same here. That's what we get. We managed to compute the amplitude of the total transmission. Transmission amplitude through both junctions. Good. Let's get probability. Let's get to probability. Okay, here it is. As we see, it does depend on the phase factor, which is accumulated between the junctions. So it's simplest manifestation of interference effect in quantum transport. Let me plot this transmission for equal transmissions left and right for different values of these transmissions. I plotted versus chi. Simultaneously, I can recall that phase depends on energy, so it could be also a plot for different energies. Transmission coefficient which depends on energy. Good. So if transmission is weak, small, right? What I see, almost no transmission, but there are peaks, very pronounced peaks, when this phase shift is just high. Good, the same picture remains if I increase transmission. If transmission is already high, the difference between maximum and minimum is small. But what is important, that this interference actually results in a very high transmission, even if the constituents were not transparent. They could have very low probability to get through. Nevertheless, the resulting structure by magics is very transmittive. All right. My traditional question, if there are Frenchmen in the audience or representatives of French culture. Nobody admits that. Okay, then my question to everybody, what are two French names which can be associated with this situation. Perhaps if you go through optics a good time, you might recall this. Fresnel, not quite. Fresnel did a lot about interference, but not for this particular setup with periodic peaks. It is called Fabry-Perot interferometer. Usually do it for waves. You just set two semi-transparent mirrors like this, and the waves propagating can get in resonance with the distance between the mirror and there is interference pattern. So Fabry-Perot system would have transmission peaks like this. And what is there on the axis is the frequency or wavelength of the light. Fabry-Perot experiment. Fine. Interference. And now what we'll get if we integrate over the phase. Integration over the phase, it's convenient. It's a way to cancel interference, all interference effects. Right, you might remember that, I guess I'm out of time. Oh, Jesus. That's always difficult with this dumb thing. You might remember that, it's a kind of cosine sine of phase difference involved. If you integrate it, corresponding coefficient is cancelled. So to get rid of interference, we integrate this expression over phase shift. And actually what we get is interesting. This is sum of probabilities to experience each of these processes. Bounce once, bounce twice, and so on. So these trajectories, they work like slits. So in fact, we have many slit experiments here. Slits differ by the number of bounces. So there is some classical term like this. But if you take into account all interference patterns between the slits, we would have full quantum answer. Right, so I told about double junction. We will revisit it soon. Let me show you an alternative way to solve the resulting equations. Yeah, I guess it's rather clear. I don't want to talk much about this. First of all, let's see how much we don't know. We consider wave which propagates from the left. There's some amplitudes here, some amplitudes here. In channels going to the left, there are amplitudes of the same kind of channel going to the right. There's transmission amplitude, there's reflection amplitude. So there are lots of unknown quantities. But we can make up equations to determine all these quantities. These equations are supplied by each scattering matrix. Take, for instance, this scattering matrix. So it relates incoming amplitudes. And what do we have for incoming amplitudes? It's 1 and B. And there are outgoing amplitudes A and R, total reflection. Same we do for the matrix on the right. As to this end, which unites these two scatterers, it's purely phase vector. So there's a diagonal scattering matrix, if you wish. So A is related to C. D is, yeah, incoming. D is, D defines B. Fine. So there is a way to kind of address problem mathematically by writing the equations, and then, well, you solve these equations, you find transmission and reflection amplitude. That can be a typical examination problem. Right, let me talk about Aharonov-Bohm ring. I don't want to go into much detail here because I'm a bit behind the schedule. Right, so let's make a circuit, and we use the beam splitters we have discussed right before the break. We take two beam splitters and arrange it as it's shown. So from two beam splitters, we made a two-terminal structure, and we want to assess transmission from here through the whole structure. Fine. Why did I do it with beam splitters? I wanted to make a loop and to put some flux into this loop. Right. So here I wrote phase vectors which are equate when you traverse these channels in different directions. You require same dynamical phase, but opposite geometric phases. Fine. So how shall I proceed? Again, I want to look at separate trajectories first and then sum them up. It cannot be done kind of analytically. Yeah, it's not convenient to do it analytically. I wouldn't present the full calculation, but let me choose some sample trajectories and discuss interference between them. Those is a pair of very simple trajectories. Yeah, so electron goes from the left to the right after either taking upper branch or lower branch. Besides, I have more complex trajectories. Let me compare C and F. Eventually, if you look carefully, you understand that the both trajectories cover the same arms, the same parts of the nanostructure. And they only differ in the, no, let's see, I need to compare. C and D, I'm sorry. These trajectories only differ by propagation in the loop. Look here, it makes it counterclockwise, and here clockwise. Otherwise, it covers precisely the same parts of the nanostructure. So trajectory C and D, I put a little bit more trajectories, but I don't want to use it. Good. So let me look at the results of interference. First, let us consider interference of the simple trajectories. Right. The answer would include the flux because they form loops, that's an Aharonov-Bohm effect, but also the difference of dynamical phase. As we see from this, the effect is periodic in flux with a period of 2 times phi naught. Also, one needs to mention that again, if I average over these phases, the result is 0. It vanishes upon averaging over dynamical phases. Fine. Let me look at these complex trajectories. Okay, I took D and E, but it's about the same. They only differ in direction of propagation around the loop, either clockwise or counterclockwise. Fine, which means dynamical phases are precisely the same for these two trajectories. And dynamical phase doesn't interfere the answer. There's only Aharonov-Bohm phase. Because of the loop, there's a factor 2 over here. So the result doesn't depend on dynamical phase. It is periodic with a flux quantum. And since it doesn't depend on the dynamical phase, it doesn't vanish upon averaging. Good. Let us see. One could write equations similar to the equations we used before. So any scattering matrix here, 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 one can also regard the scattering matrix, diagonal scattering matrix, supplies a set of equations for incoming and outgoing amplitudes. Okay, we did so that. I can write the result for symmetric splitter, for symmetric situation. And let me show just a couple of curves. These curves are two different curves. They are periodic with a period of two flux quantum. They differ in dynamical phases. So you see very varying pattern, which is periodic into pi. What will happen if one averages over all possible phases? Eventually, averaging over curves with a period 2 gives you a curve with a period 1. It can be explained by what I told you before, that there are special interference, that special trajectories, interference between which is not affected by dynamical phase. Fine. This is what we learn about Aharonov-Bohm effect in the ring. Let me get to experiments. As we see, the experiments are rather old. They've been made in 80s, and the technology of that time was not very advanced. Although technology evolves relatively slow, there's still technological tricks which have been invented 50, 70 years ago. They're still in nano lab. But that still was rather primitive technology. And there was a technological trick which allowed the authors to see, well, with some fantasy, you can see oscillations which depend on magnetic field. Good. What was the system? The authors have taken, they wanted to make a small structure, and they have taken a whisker, a special insulating crystal, which can be very thin and long. They took this whisker and they evaporate a cylinder of tin upon that, which was pretty long. So that was a fraction of micron, but that was perhaps 1 millimeter long. Good. Then they just put two contacts. They measure the conductance, and simultaneously they change magnetic field in this direction. Sure, they see the oscillations, and you can see if you expect the caption, they have period of a single flux quantum. Who can explain why? Right. As it follows from my story, this period signals averaging over dynamical phases. There's no some extra device which averages the setup over the phases, but the fact that the sample is long and there are many possible trajectories which can go around the field, the hole where magnetic field is present, that the self-averaging over these trajectories. They have different magnetic field, different dynamical phases. So if you sum up over all trajectories, dynamical phase is gone. That's what they see. All right, and that was a time of competition between Soviet Union and United States, very symmetric configuration. And apparently Americans wanted to provide some response. And it did not take much time to provide one. And American technology was superior by the time, so that they did it differently. Instead of making a long, elongated cylinder, they make it very flat. So they just made a cylinder by evaporating very thin film of the metal onto an isolated substrate. That was the actual device. Right. And they do the same. They measure the resistance as a function of magnetic field. What they see is that I see very, very random signal, which you might regard as, just electric noise. But it was completely reproducible. So that if they sweep magnetic field in one direction and return in the other direction, the picture is completely reproducible. To their astonishment, right, and this is a pattern which doesn't look like regular oscillations. One can kind of make Fourier analysis and analyze typical amplitudes. Typical amplitudes okay, that's zero magnetic field, nothing to look about. This correspond to periods of 2 phi naught, 4 phi naught, and so on, right? So 2 phi naught indicates that we have fluctuations which do depend on dynamical phase. Why do we see them? Because the cylinder was flat. If you wish, the device was much smaller. That was the response. So it is a result of interference between trajectories A and B, as I told you, and I guess my time is up. I hope you enjoy this story about interference. Let me stop um, the camera.